All right, welcome to the Explainer. Today, we are looking at a piece of tech that's making a pretty wild claim. They say they can do the impossible, basically shrink the time it takes to find new medicines from days down to just a couple of seconds. And the craziest part, they're doing it on a regular old laptop. So let's just start with a question that really gets to the core of what we're talking about today. What if the power of $1 billion cutting-edge pharmaceutical lab could literally fit inside the laptop you're probably watching this on right now? Okay, to really get why this is such a game changer, we have to talk about the challenge this thing just went up against. In the world of drug discovery, there are hard problems, and then there's the final boss. And here it is. This is HIV-1 protease. For decades, this has been the gold standard, the ultimate test for any drug discovery software. It's just a notoriously complex, tricky protein that scientists have poured years into studying. The rule is simple. If your software can accurately map this, it can probably map just about anything you throw at it. And that's really the crucial point here, right? Cracking HIV-1 protease isn't just checking a box. It is the validation. It's what proves your whole system is ready for the big leagues. You beat this boss, you can take on almost any disease out there. All right, now let's get to the results. And this is where the story just gets absolutely wild. To really feel the shock of the number I'm about to show you, we first got to look at how this stuff is normally done. So, the status quo, the way it's always been done, involves these massive, expensive supercomputer clusters. We're talking rooms filled with servers costing millions of dollars. And you know what else it involves? A lot of waiting. A scientist will kick off a simulation and then they go home. They come back hours, maybe even days later, just to see the results. PRISM Fold, it finished its entire analysis of that final boss, HIV-1 protease, in 2.63 seconds. No, that is not a typo. I'm going to say it again. 2.63 seconds. That is literally less time than it took me to say that sentence. Yeah, I know what you're thinking. How is that even possible? This number just seems to shred the rulebook for computational biology. Going from days to seconds, how in the world did they do that? Well, believe it or not, the answer is actually even crazier than the number itself. And that brings us to what might be the most mind-blowing part of this whole story. Because it's not just about how fast it is. It's about who can now use that speed. So get this, that 2.5-second result, it wasn't run on some multi-million-dollar server farm or a classified government supercomputer. Nope, it was run on a single, off-the-shelf, consumer-grade laptop, the kind of thing you could go buy right now. This is the detail that changes the entire game.
Just look at this comparison. It's a total paradigm shift. The old way, you needed supercomputer clusters. The PRISM Fold way, a consumer laptop. The old way took hours, sometimes days. Now, 2.63 seconds. And the cost? We're going from millions of dollars in hardware to basically zero. The barriers of cost, time, and access, they're just gone.
Just stop and think about the implications of that for a second. This means a student in their dorm room can now do the kind of work that used to require a $1 billion lab at Pfizer. A small startup, a researcher in a country with limited resources, they can now compete. They can run experiments that until now were completely out of reach. The gates to innovation have just been blown wide open. Okay, so the big question remains, how on earth is this possible? Well, the secret sauce is a really clever new approach. It's what they call a hybrid engine, and it basically takes the best of two totally different worlds and smashes them together. See, up until now, tools for this kind of work had a big trade-off. You had your physics-based models, which are super accurate, but man, are they slow. Then you have the newer AI-based tools. They're lightning fast, but they have a problem. Sometimes they just make stuff up. They hallucinate results that aren't real. PRISM Fold basically says, why choose? It finds a way to be both fast and accurate. It's kind of like this brilliant 3-step process. First, you have an AI that acts like a detective. It uses something called active inference to quickly scan the scene and find the most promising clues, the best places to look on the protein. Then, step 2, the physics expert comes in. This engine double-checks the detective's work, making sure everything is physically accurate, right down to the individual atom. And that third piece, that's what makes the whole thing happen in the blink of an eye. And that speed comes from a clever bit of engineering called a zero-copy architecture. Think of it like this.
Most computers are like a city with a bunch of traffic lights and intersections. Data has to constantly stop, get copied, and move again. It creates bottlenecks. Zero copy is like building a dedicated, nonstop superhighway for the data. It moves directly between the processor and memory on the GPU, so there's never any waiting in traffic. It's just pure, raw calculation speed.
So, okay, we've established it's insanely fast, and it runs on a laptop, so it's super accessible. But here's the billion-dollar question. Is it actually right? Because let's be honest, speed means absolutely nothing if the answers are wrong. Let's look at the proof. So, the system scanned the virus and found 15 potential pockets. You can think of these like little keyholes where a future drug, the key, could fit. But it didn't just find them, it analyzed each one. And the very best one it found had these stats, a specific volume and a druggability score of 0.650, which led it to a very clear conclusion. This spot is druggable. And this, right here, is the money shot, the absolute most critical piece of validation. That best pocket it found, it wasn't just some random spot. It was the correct one. It pinpointed the known active site. The exact lock that scientists have known for years is the key to shutting down the HIV virus. It didn't just find a lock, it found the lock. And let's talk about that druggability score for a sec. That 0.650 isn't just a random number. It's basically a confidence score on a scale from 0 to 1. In this world, anything over 0.6 is considered a high confidence, A+ target. So PRISM Fold didn't just say, hey, here's the spot. It said, here's the spot, and we are very, very confident this is a great place to design a drug for. So when you put it all together, the system basically aced its final exam. It passed every single scientific sanity check you could throw at it. Did it find the right active site? Check. Did it avoid making up silly, nonsensical pockets? Check. Were its final scores realistic? Check. The bottom line is the results aren't just fast, they're scientifically solid. So what's the big takeaway from all of this? This isn't just a small step forward. This isn't just a faster version of an old tool. What we're looking at is something people are calling a compute collapse. It's where the huge, towering barriers of time, of money, of access that have defined drug discovery for generations are basically collapsing down to near zero.
And that really just leaves us with one final and kind of profound question to think about. When the power to discover life-saving medicines is no longer locked away in billion-dollar labs, but is available to anyone, anywhere, with just a laptop, what's next? What will we cure?